Okay, here's part 4 of today's lectures. This will cover the second of Kirchhoff's laws or Kirchhoff's rules when analyzing circuits. I'll also do the bulk of the example problems here as well. When is necessary, go ahead and pause the film such that you can then write down the problem in your notes. Okay, so Kirchhoff's laws or Kirchhoff's rules. Okay, the first of which I already briefly mentioned, and that's junction rule. The total amount of current going into a junction has to be the same as the total amount of current coming out of the junction. And then the second is referred to as loop rule. Whenever you start at some point within a circuit, and then you traverse a loop such that you end up back where you started, the total potential difference has to be equal to 0. If it wasn't, it would violate conservation of energy. So for example, let's say that I have a very simple single loop circuit. So here's a battery with voltage V. Once again, we'll ignore EMF and internal resistance here. Okay, and then right here is just a single resistor like so, R. And then we're going to follow the conventional current here as it flows from high to low potential. Okay, what I'm going to do is I'm going to start right here and then add up all of the potential differences in a clockwise fashion as I follow the current such that I end up back where I started. When I do, the total amount of potential difference has to be equal to 0. All right, so let's go ahead and follow the current here in a clockwise fashion here on this simple diagram. I'm going to do so by starting here, and then I go across the battery, as we say, from low to high potential. So then therefore the final value of the potential is greater than the initial value, so the potential difference V is a positive number for that reason. Okay, and then we follow the current here as it falls across the resistor from high to low potential. Okay, the potential difference across the resistor from Ohm's law is just equal to I times R. But if we go from high to low potential, the potential difference then therefore final minus initial is a negative number for that reason. And then I end up back where I started, so then therefore the total potential difference is equal to 0. It actually doesn't matter, however, which way I go through the circuit. As long as I follow loop rule, the potential difference has to be equal to 0, and then therefore I ultimately end up with the exact same equation. So for example, let's say I traverse this circuit, once again starting here in a counterclockwise fashion. So what I do, I'm going against the current, as we say. So if I go against the current across the resistor, in this case, I'm going from low to high potential, so then therefore the potential difference IR is a positive number. Once again, final minus initial is potential difference. If I go that way, I go from low to high potential, so then therefore the final value of the potential minus the initial value is a positive number for that reason. Okay, and then I go across the battery in this direction. So when I do, I go from high to low potential. So then therefore final minus initial has to be a negative number. So then I end up back where I started. So then therefore the total potential difference is equal to 0. Obviously this equation here is the same as this equation here. You just have to be careful of your positive signs and negative signs when doing this, but ultimately regardless of which way you go through the circuit, you should end up with the same equation. Okay, now let's go ahead and take a look at the examples here, the bulk of the examples for chapter 26. So go ahead and pause the film here at this point and copy down the first example. The first example involves 4 circuit elements, and then we're going to see if we end up breaking a fuse when we place all of these circuit elements in parallel with respect to each other. Okay, so let me read the first problem to you. 4 circuit elements consisting of a 100-watt light bulb, an 1800-watt electric space heater. Space heaters are very dangerous for this reason, by the way. A 350-watt stereo and a 1000-watt hair dryer are all connected at your house in parallel to each other with respect to a 120-volt line. That's a VRMS, but we'll just write it as a direct current calculation. And then a fuse rated at 20 amperes is placed in series with all the other circuit elements. Okay, when we have all the other circuit elements on, will this break the fuse? Okay, let's picture this problem in the sense that we just turn one object on or one circuit element on after another. Let's see what happens first of all when we just have the light bulb lit. Okay, now this circle right here, I'm going to use that circle to represent what is called the fuse. And then right here is my first circuit element. This right here is the light bulb. As there's resistance R1 associated with it, right here is the voltage V, and then we have the current flowing like so. Okay, now the voltage V is given to us as 120 volts, and we don't know what the resistance is here associated with the light bulb, but we are given that the power that is necessary to operate it. So we'll call that P1. This right here is equal to 100 watts. Okay, now the voltage across this resistor is the same as that of the battery. So therefore, I'm going to go ahead and write the P1 here as that voltage squared divided by the resistance R1 associated with the light bulb. And now let's go ahead and just calculate what the resistance of the light bulb is by doing the following. Cross multiply, like so. And now let me go ahead and find that number. I'm going to use this number then to calculate the amount of current that is going through this resistor. Ultimately, that's the same as the conventional current I here for the entire circuit because we only have this one thing on. All right, so 120 squared and then divided by 100. And this comes out to be 144 ohms. Like so. Okay, and now that voltage is equal to I times R1, so let's go ahead and calculate the current I. So V over R1. So then therefore that's going to be equal to 120 divided by 144. 120 divided by 144. Okay, and that comes out to only be 0.83 amps. So that's the total amount of current that is flowing through the circuit right now. That's not going to melt this fuse or triple switch here. In other words, we could safely operate this light bulb. Okay, now we're going to turn on the space heater. When we do, the amount of current that we're ultimately drawing through the circuit is going to increase. So here's then what happens when we now also have the space heater on. All right, so here's the light bulb from before, R1. And now right over here is the space heater, R2. Right here is the current I, voltage V, and then junction rule comes into play. We're going to have here an I1 and an I2 like so. So I is equal to I1 plus I2. So I need to calculate these two values of I here. Now the I1 is going to be the exact same thing as it was before on the top board for just the light bulb all by itself. That is, it's going to be 0.83 amps again. The reason for that is because the voltage V here is the same as that of the battery. So we can go ahead if we wanted to and calculate the resistance again. It would be the same value as before, of course. And then therefore we can calculate the current. In this case, it would be the current I1, however. So it's still 0.83 amps. But now we also have current here flowing through the electric space heater. So now we have P2 for the space heater is given to us as 1800 watts. And now I'm going to go ahead and calculate the resistance. We'll call it R2 across the space heater by using this expression. So R2 is the same voltage squared, but now divided by P2, like so. So then therefore, 120 squared, and then divide that then by 1800. And this comes out to be 8 ohms. So then therefore, using Ohm's law now, we can go ahead and calculate the current I2. So the I2 is going to be the voltage V divided by R2, like so. So 120 divided by only 8 ohms, and this comes out to be 15 amps. So by turning on additional circuit elements in the parallel circuit, you then overall draw more current. Right now, the total amount of current I here is going to be 15.83 amps. Like so. The greater the total amount of current that is being drawn in a circuit, therefore, the hotter essentially the wires then heat up due to the resistance then. So as the wires heat up, as you draw more and more current, then you start to run the risk, for example, of say right here, melting your wire or ultimately then causing something to catch on fire. Obviously, you don't want to have that happen. This then means that what we do is we build into this large parallel circuit that we're beginning to construct here what is called a fuse. The fuse is either a small piece of wire that melts when you draw too much current I, such that it then breaks the circuit, and then therefore nothing catastrophic happens, like something catching on fire or something melting or something like that. Sometimes the fuse is what is referred to as a bimetallic strip. A bimetallic strip are two pieces of metal that heat up, but they heat up such that they expand at different rates. And then therefore that causes the bimetallic strip to curl in one direction like so, which then breaks the circuit. This is the switch that you see on a circuit board. So then what your father, for example, then has to do when you turn on too many things in the house and all of a sudden the power goes out, is he has to go outside to the fuse box, usually mounted on the side of your house, and then flip the switch back into position. Before he does that, however, you have to make sure that everything is turned off, and then therefore you can start to turn things on once again after he has made that switch. So that's what the fuse ultimately is in a realistic situation for a house. It's a bimetallic strip that expands in one direction as it heats up. That then breaks the circuit, and then you go outside and you flip it back into place like so. Okay, now let's see what happens when we keep this series or keep this parallel circuit here, but now we hook up the next element. Now we hook up to it the stereo. Okay, I'm going to go over and move to my other board for that reason. All right, so here's the R1 from before. Here's the R2. Okay, once again, let me go ahead and draw the fuse here. This is a circle like so. Okay, now right here is the R3. And then for stereo, P3, we'll call it, is given to us as 350 watts. So the total amount of current I here then splits into an I1, an I2, and then ultimately an I3, like so. So the goal here now is to calculate the I3. The first thing that we'll do is we'll find the resistance R3. So R3 in this case is going to be V squared divided by P3. So let's go ahead and calculate that. So 120 squared over 350. And that comes out to be 41.4 ohms. And once again, we'll use a little bit of Ohm's law here to find I3. And it's going to be V divided by R2. So 120 over that resistance. And that comes out to be about 2.92 amps. So then therefore add that to the I1 and the I2 from before to get the total amount of I. All right, so I1 plus I2 from before was 15.83. So 15.83 and then plus 2.92. So we're getting rather close now. And this is 18.75 amps. This is still less than 20 amps, however, so you can still safely operate this circuit. Once again, the more things that you turn on, the greater amount of the total current that is being drawn. That can then cause things to melt, for example, over here in this circuit. Obviously, you don't want to have that happen. Okay, and then therefore, lastly, we turn on the 1,000 watt hair dryer. You could probably guess what's going to happen now. This is ultimately going to cause the total amount of current to be greater than 20 amps, and then therefore the circuit will break. All right, so let me just go ahead and adjust this diagram here to illustrate. So here's the R3 from before. Okay, and then right here is the R4. The power associated with that device is 1,000 watts. Okay, so we're going to have here once again I3 from earlier, and then I4. So now let's go ahead and first of all figure out the resistance R4. We'll do so by once again using the same sort of expression, V squared divided by P4 in this case. So that works out to be 120 squared over 1,000. Okay, that's about 14.4 ohms, and then using Ohm's law, we'll now find I4. That's R4, so 120 divided by that, and that current comes out to be 0.33 amps. So then therefore the total amount of current here, I is I1 plus I2 plus I3 plus I4, add it all together. So here's the first three, 18.75 amps from before, and then add to that the additional 8.33, and then therefore you end up here with a total current I of 27.08 amps. So this is greater than 20 amps, and the fuse breaks the circuit. So when the power goes off in your house, what you do is you immediately turn everything off, let it all cool down for a couple of minutes, then you go outside to the fuse box, and you then go ahead and trip the switch back to its original position. Okay, to show you that, by the way, I'm going to show you my fuse box here in this classroom. It's actually on the other side of the wall in my storage room. So let me move some stuff out of the way. Grab the computer. Point seven, and then right there is the fuse box associated with the electrical outlets. And of course, you have one of these. Okay, let me move back. Like so. Okay, go ahead and pause at this point while I go ahead and erase the board then, and then I'll go ahead and get on to the additional problems. There we go. Okay, still recording. Okay, very good. Okay. Okay, so the second problem is an equivalent resistance problem. Okay, it references a specific diagram. I'm just going to go ahead and draw that diagram on the board for you. We have a series of resistors, all with a resistance of 1 ohm. Okay, the actual diagram from my notes looks like this. So I stuck another one down here. Like so, and then we have other stuff over here, whatever it happens to be. Okay, so we've got these resistors here, R. Each one of these R's here is equal to 1 ohm. Go ahead and then calculate the equivalent resistance. Well, this is kind of like the equivalent capacitance problem that I did a while back. Basically, what you do is you kind of start small and then work your way outwards. So I'm going to go ahead and find, first of all, the equivalent resistance here of these two guys, which are in parallel with respect to each other. We're going to call this R equivalent 1. Okay, because they're in parallel, it's the 1 over relationship, not the addition relationship like it was for capacitance. It's the 1 over relationship. So 1 over R equivalent 1 is equal to 1 over R plus 1 over R. Remember that all the R's here are the same. So I just have here a total of 2 on the right-hand side of the expression. Take the reciprocal, and then therefore R equivalent 1 is equal to 1/2 ohm, 5 ohms. Okay. Okay, I suggest that you pause and just redraw the diagram. I'm just going to erase here. Like so, and now right here is our R equivalent 1. Okay, and then this R equivalent 1 is in parallel with this guy over here. So then therefore these guys here act as a single resistor. We'll refer to this as R equivalent 2. Once again, they're in parallel, so it's the 1 over relationship. So 1 over R equivalent 2 equals 1 over R equivalent 1 plus 1 over R. So this is 1 over 1/2, which is a total of 2 plus 1, which is 3. Take the reciprocal, and then therefore R equivalent 2 is equal to 1/3 ohm. Like so. Okay, once again, pause and redraw the diagram if necessary. Then this then right here. This then behaves as a single resistor, R equivalent 2. Okay, and then lastly, the total R equivalent that we're trying to find is now going to be these guys added together because they're in series. All right, so here's the answer then. R equivalent, this is what we're trying to find, is R equivalent 2 plus R. So this right here is 1/3 plus 1 for a total of 4/3. Like so, typically examples like this are pretty easy to do. Okay? Okay, and then we'll take a look at a couple of loop diagram problems. We'll take a look at a single loop first, and then we'll take a look at a multiple loop situation. With respect to multiple loop situations, usually it's just 2 loops that you have to mathematically deal with. Okay? All right, so here's the first of the 2. Okay, once again, pause the film if necessary. I'm going to go ahead and erase. Okay, so now a single loop example, C diagram, we're given the following. We're given an EMF in this case of 6 volts, R1, R2, and R3 of respectively 1, 2, and 3 ohms. Find the current and the rate of heat loss in each resistor. Okay, so very simply, we have 3 guys here in series. All right, so right here is the EMF, like so. We'll ignore internal resistance in the battery. Sometimes how problems are stated vary from situation to situation. Okay, and then we've got these guys like so here in series. Current I, and then R1, R2, R3, like so. There's multiple ways to do these problems here, as you'll discover as you start mathematically screwing around with them. Okay, we're given the epsilon here. By the way, that's an epsilon. It is 6 volts. R1 is 1 ohm. R2 is 2 ohms. R3 is 3 ohms. Like so. Okay, so I'm going to go ahead and just set a loop rule here in order to find the current. In order to do so, it doesn't matter where I start in the circuit to do this process. Let me just go ahead and start right here, and then just go clockwise around the loop. And when I do, I'm going to follow the current as I go. The first thing I do here is I go across the EMF from low to high potential. Therefore, the potential difference is epsilon, positive number. And then we go with the current across each resistor. So then therefore, final minus initial is going to be a negative number as we go with the current. We fall from high to low potential across each resistor. So minus I times R1, minus I times R2, minus I times R3, and then I end up back where I started here once again. So then therefore, the total potential difference is 0. If I wanted to, I could go ahead and find the equivalent resistance of these 3 guys in series. That would just be R1 plus R2 plus R3, and you ultimately end up with the exact same expression anyway. And now we just solve here for I. So let's go ahead and move some stuff around and do some factoring as we do. Like so. Okay, right there in parentheses is our equivalent for this situation. And then I just go ahead and divide now to find the current I. All right, so current I is epsilon divided by the sum of the resistors, or resistances. So a total of 6 volts and then divided by a total of 6 ohms. So this just comes out to be 1 amp. Okay, and then the rate of heat loss in each resistor. This is the P loss calculation that we'll refer to it as. So P loss is going to be I squared R1 for the first object or the first resistor. So let's go ahead and find that. So 1 squared multiplied by 1 ohm is just 1 watt. Okay, and then P loss 2, we'll call it for the second resistor. Same value of the current I, and then squared, and then times R2. So 1 squared times 2 ohms, this is 2 watts. And then lastly, P loss for the third. Okay, this is going to be I squared times R3. So 1 squared times 3 ohms is 3 watts. Like so. So pretty obviously, a single loop circuit is easy to do. Okay, and then the last example for today's lectures will be a multiple loop circuit problem. This will involve 2 loops. Okay, so pause if necessary. I'll erase the board here. Okay, so a multi-loop circuit example. We'll see the diagram. I'll draw it out for a moment in just a moment. Find the current through each resistor given epsilon 1 is 5 volts, epsilon 2 is 10 volts, and then I have resistors 1, 2, and 3 ohms respectively. And then the diagram that goes with this is drawn in the following way. Okay, so here's epsilon 1. Here's epsilon 2, like so. Okay, and then I've got 3 resistors here. 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 And here. Like so. Okay, and then the values here are as follows. This is R1, 1 ohm, R2, 2 ohms, and R3, 3 ohms. Okay, and then I've got my 2 EMFs here. They are 5 and 10 volts respectively. This right here is 5 volts. This right here is 10 volts. Okay, so how do you analyze such a circuit? Well, what you just simply do is assume a direction associated with the current, and then just apply the rules to calculate the values of the current. And when you do, you'll basically end up with, in this case, 3 equations and 3 unknowns. All right, so let's say that we have right here, for example, a current I3 that is passing through this resistor, and then that current I3 reaches this junction. And when it reaches this junction, it splits into 2. So there's going to be an I2, we'll say, going that way, and an I1 going that way. So all I'm doing here is just making an assumption, and that's all. And let's go ahead and apply junction rule. So when I apply junction rule right here, we're saying that I3 coming into that point, like so, splits into I1 plus I2. Like so. Okay, that's the first of ultimately 3 equations and 3 unknowns. Okay, the other 2 equations. The other 2 equations are going to be loop rule. We're going to set up loop rule for this side of the diagram, and then secondly for this side of the diagram. And it doesn't matter where you start on the diagram, and it doesn't matter then how you traverse the diagram, either clockwise or counterclockwise. So for example, let's just start right here. And now on the right-hand side, let's just go around clockwise like so. So the first thing that I do is I go across the EMF from low to high potential. So then therefore the potential difference is just the positive value of epsilon 2, like so. And now I go with the current I3 across this resistor. So then therefore the potential difference is I3 R3, like so. And then I get to here, and then I go this way. And now I'm going with the current I2 across this resistor. So then therefore the potential difference is minus I2 R2, like so. And then I end up back where I started. 0. Okay, and now let me go ahead and start right here again, and now go this way across this loop over here on the left-hand side. So when I do, I go first of all from low to high potential across this EMF. So then therefore the potential difference is positive epsilon 1. Okay, and now watch this. I'm going against the current I1 across this resistor. So then therefore, if I go against the current, I'm going from low to high potential. Therefore, the potential difference I1 R1 is a positive number. So, and then, oops, not equal to 0. Sorry, I'm not finished yet. Okay, and then keep going this way like so. And now I go with I2 across the resistor R2. In this case, we're going from high to low potential. So the potential difference then therefore is a negative number. So, and now I end up with 3 equations and 3 unknowns. The easiest way to deal with these types of problems, quite frankly, is that at this point, just immediately start plugging in the numbers. So let's just go ahead and do that. And to do so, I'm going to use my loop rule expressions. All right, so let's take a look at, first of all, this guy right here. So I've got 5, and then plus 1 times I1, and then minus 2 times I2. So, okay, and then take this guy here, plug in the numbers. This right here is 10. Okay, and then minus 3 times I1. So, and minus 2 times I2. I3, excuse me. There we go. And then minus 2 times I2. so. Okay, I'm going to erase the things that I don't need at this point, so let's get rid of this. Let's get rid of that. And now I have here 3 equations and 3 unknowns. So what's the easiest way to do this? Well, as you can see, this is definitely a bit of a mess. Let's see. How do I want to do this? Let me go ahead and take this I3 right here, which is I1 plus I2, and plug it into here. Like so. Let's go ahead and simplify this. Okay, minus 3I2 minus 2I2 is minus 5. I2 like so. Okay, let's take this guy here and then solve it for I1. And then I'll go ahead and plug it into there. And when I do, I'll only have I2 as an unknown. All right, so move that to that side, move that to that side. So take that then and plug it into here. Like so. Okay, now do the math. So 10 minus 6I2 plus 15, and then minus 5I2, like so. Okay, this guy right here adds up to 25. These guys here add up to a total of 11I2 when I move it to the other side, like so, and now divide. So I2 is 25 over 11 amps, whatever that is. So 25 over 11, that comes out to be 2.27 roughly. Like so, and notice that I got a positive number here. When I got a positive number, what that means is that the direction of I2 on the board, in fact, is correct. If you end up slogging through all your algebra here, and you solve for a current I and it ends up being a negative number, all that simply means is this in the opposite direction of what you guessed up on the top board. So let's see what happens for the other values. Okay, right here is I1. Let's now go ahead and find that. So 2 times I2, so I2 is 2.27 amps. So 2 times 2.27. Okay, and then minus 5. And I, in fact, get a negative number here in this case. Negative 0.46 amps. So then, therefore, because I got a negative number, what that means is that I1 actually goes in the opposite direction of what I had guessed. Okay, let's go ahead now and find I3. That's last. We'll do so by just adding up I1 and I2. Now, when I add up I1 here, you do include the negative sign. So negative 0.46 amps plus 2.27, and that ends up being a total of 1.81 amps, like so. So basically, you just set up the 2 rules, junction rule and loop rule. You just assume directions associated with the currents and then calculate. And then whatever your answer ends up being, positive or negative, that then tells you the values and in which way the currents flow. Okay? Okay, this right here actually completed for us the bulk of chapter 26. There's only one short section to chapter 26. I'll get to that, however, next time in class. I'll also give you some information about the next exam, which is on the horizon. It will cover chapters 24, 25, and 26. And of course, it's going to be a take-home exam. Today's shirt was Skeleton Wedge. Have a nice day. See ya. Stay safe.